Hello viewers, welcome to the lecture series of algorithms. Myself Dr. Preeti Jagwani. I am from Department of Computer Science, Aryabhat College, University of Delhi. Today's topic is DFS, that is depth first search. So now let me start with what actually depth first search is. Depth first search is one of the traversal idea or one of the traversal mechanism of graph. And graph traversal, as you all know, is nothing but a process of visiting each and every edge and visiting each and every vertex and edge only once. There should not be any repetition. So visiting all the vertices of a graph is traversal, and within that traversal mechanism we have various ideas of traversal, various types of traversal, in which we have breadth first search and depth first search. So breadth first search we have already considered in our previous lectures. So today's topic is depth first search, and within this lecture we will be focusing on depth first search. So this depth first search DFS, let me build a platform for it, that why and where this DFS traversal is required. So in terms of algorithms, if we talk about that, in a weighted graph your DFS traversal is going to give you minimum spanning tree. If you can recall the breadth first search is not going to give you minimum spanning tree in case of an weighted graph. In case of unweighted graph it can give you, but in case of a weighted graph it is quite difficult, or DFS is preferred if you want to have MST, which is minimum spanning tree, in case of a weighted graph. And for single source shortest pair your BFS is suitable, but if you find all pair shortest path tree, then you have to have DFS as your traversal mechanism. Another idea, if we want to detect cycle in a graph, that whether there is a cycle present in the graph, yes or no, then DFS mechanism is there to help us out. And if you have some decision trees, or let's say games playing or solving the puzzles which are having only one solution, for example maze problems, so all these problems can be solved, decision trees or these games and all these puzzles with one solution like maze can be solved with the help of depth first traversal. So depth first traversal is in a simpler terminology, I can say, if there exists a path between two vertices in a graph, these two vertices can be any two vertices, and if there exists a path between two given vertices, to find that path, DFS is the idea. Another application of DFS is topological sorting. So topological sorting is basically scheduling of jobs with respecting along with the respecting given dependencies which exist among the jobs. So we have n number of jobs in which, let's say, job n1 is dependent on job n2 and job n2 is dependent on n3. So in which sequence we need to schedule these jobs in order to respect the dependencies, that kind of sorting is known as topological sorting. That topological sorting also you can achieve with the help of depth first traversal. Another application is finding strongly connected components of a graph. So strongly connected graph is basically a directed graph, can be said that it is strongly connected if there is a path from each vertex in the graph to every other vertex. So if we need to determine that whether the graph is strongly connected or not, that means is there any path from each vertex in the graph to every other vertex, again DFS is the key. So basically along with so many applications of depth first search traversal, what does or how this depth first traversal is going to work. So as the name suggests, depth first. So in breadth first traversal we have covered our graph, if you remember, layer wise or level wise you can say, but here a graph has been traversed in a depthward motion. And we need to use stack in order to keep track of the next vertex which is to be visited. And this stack is also going to give is also going to provide us help when there is any dead end in the iteration. So, if there is any dead end in the iteration, that means we cannot move depthward in that particular using that particular branch, then that is what you call a dead end, and if such dead end occurs, we need to backtrack. So, all these implementations or all these functionalities can be achieved with the help of stack as a data structure here. So, if you remember, in breadth first search we have used queues as the main data structure, but in depth first search we will be using stack as a data structure. So, just let me give you a glimpse of how this depth first search operates. So, in breadth first search, similar as to breadth first search, we are going to use one or we are going to choose one starting vertex. Let us say in the given graph, I have chosen the starting vertex as S, and then I will keep on going in the downward, in the depthward direction. So, from S I can go either with A or B or C. So, let us say I am going with A. So, S to A, then from A I do not have any other vertex which is unvisited except D, although there are two vertices which are adjacent to A, one is S, another one is D, but we need to keep a track of visited vertices, and then as S is already visited, you remember that we have started from S only. So, from S we have jot down to A, and then from A we are coming to D, and then from D again the unvisited vertex which is available is G. So, we will be going to G. Now, from G, if you can see, now please notice here that graph is undirected, it is not having arrows or direction of edges. So, from G, if you consider the adjacent vertices, we can move, either we can move to E or we can move to F. So, whatever is the choice we can move to. Let us say we move to E. Now, from E the only path available to move downward, although it is showing here as upward, but this is actually a downward path if you consider it as the depth wise thing. So, from E you can go to B also, but now from here, from B we can always go to S, but S is again a visited vertex. So, now in a way we have at a dead end in which we cannot move further in the depthward direction. So, what we need to do? We need to backtrack. So, in order to backtrack, we will backtrack from B to E and check whether there are any vertices which are adjacent to E and they are unvisited yet. We do not have any such vertex because E is connected to B and G, both are visited vertices. So, we again backtrack, and this backtracking is going to take place with the help of stacks only. So, from E we again backtrack to G, and then we repeat the same process, that whether at G we have any unvisited adjacent vertices. So, yes, here we have the unvisited adjacent vertex which is F. So, again we will go to F, and then from F the unvisited vertices available is C. So, a DFS algorithm is going to give us the output in the following fashion, which says S, A, D, G, E, then B, F and C. So, here we have backtracking, or we have taken a move which is in the backward direction from B to E and then from E to G. So, this is what I have given you a simple idea of, or I can say a macro level idea of how to go about the depth first search of depth first search traversal in a particular graph. So, we can let us consider this with the help of a example in a systematic manner, step by step. But what is the basic idea of this DFS? So, basic idea says you need to visit the visit a unvisited vertex which is unvisited. You keep you mark it as visited. You need to mark it as visited. That means you can say you need to display it and then you need to push it onto a stack. If no adjacent vertex are found to it, we can pop the vertex from S as we have done here in the case of B and E, and then it is going to pop all the vertices from stack which do not have adjacent vertices, and we will keep on doing the same thing. We will keep on pushing the vertices as soon as long as we are getting adjacent vertices, and whenever we stop getting adjacent vertices, that means we have reach a particular dead end that you cannot move in the depthward direction anymore. Then you start the backtracking thing. So, this is what the idea, the basic idea behind depth first search traversal is, and please remember that within this we need to keep a track of all the visited vertices. Now, similar to breadth first search, this is very necessary because we do not want to get into the loops. If we are not going to keep a track of visited vertices, we will definitely going to end up in moving on in the loops or in the cycle if they are available in the graph. So, in order to avoid that graphs, in order to avoid that loops or cycle, we need to keep track of all the visited vertices. So, now let me consider one complete graph and let us try to see the DFS implementation onto that particular graph along with the contents of stack in a step by step manner. Let us say for example, you have a particular figure as shown here, which is an undirected graph of 5 nodes. The nodes are S, A, B, C and D, and initially your stack is naturally empty. We will keep on filling the stack, we will keep on pushing and popping the elements from it or onto it. So, let us start our depth first search from the you can say the vertex S. So, now from S the adjacent vertices are A, B and C, all the vertices are adjacent. So, as soon as we will keep on we have picked in a way the vertex S, we mark it as visited and we will push it onto the stack. So, now let us say our S is stack is having S as its the only element. Now, we will look for the adjacent vertices of this S. So, where can we move? We can move either to A or to B or to C. So, let us choose normally in an alphabetical kind of fashion, but this is not a constraint, you can choose anyone. Now, let me choose A. So, on choosing this A, what are the operations or what are the steps I need to perform? That is, first of all, I have marked S as visited, pushed it onto the stack, and I need to explore any unvisited adjacent node from S. So, in this for this I can pick any A, B or C. Let me pick A. So, the moment I am going to pick A, that A is going to be on top of the stack. That means, I have pushed that A vertex onto the stack thing. So, we need to mark A as visited, we have pushed it onto the stack, and again we will repeat the step that we need to explore any unvisited adjacent nodes from A. So, now from A, as you can see in this figure, both D and S are unvisited. Sorry, both S and D are the adjacent vertices of A, but the vertex S is already visited. So, we are keeping a track of visited vertices. So, we are not going to process S, instead we will be processing D. So, in order to process D, we will mark it as visited and place it onto the top of the stack. So, now here you can see in the figure that contents of stack are D onto the top, followed by S, and then followed by S. So, in top to bottom fashion, I can read stack as D, A and S. Now, you can see figure that from D we can move onto either onto B or onto C, because or we can move on from D to A also, but A is again a visited vertex. So, we have visited D, pushed it onto the stack, and the adjacent B and C which are unvisited. So, I am again taking B. So, the moment you encounter an unvisited vertex, you are going to push it onto the top of the stack. So, now stack is having B, D, A and S, and the visited vertices are the already visited vertices which depth first search traversal has already completed is S, A, D, B. Now, you can see carefully that what to do if we have already onto the vertex B. The only or the adjacent vertices of B are S and D, but these two vertices are already visited. That means we need not to process S and D both, because they have already processed. In case if we are not keeping a track of visited vertices, we will end up processing either S or D repeatedly, and then we will be in a loop of S, A, D and B. We will keep on moving into this particular loop, but fortunately we have maintained track or a status of visited vertices. So, visited vertices, all both the adjacent vertices which are S and D of B are already visited. So, in a way now we have onto a dead end, we cannot move in the deftward direction any more. So, the moment you encounter a dead end, as B does not have any unvisited adjacent node, we need to pop B from the stack, and as we pop the B from stack, what is available onto the top is D, and then we check the vertex D that whether there is any unvisited vertex which is adjacent to D. Now, the vertices which are adjacent to D are A, B and C, out of which A and B are already visited. So, only unvisited vertex which is available is C. So, we will keep on we keep on pushing this vertex, this unvisited vertex onto the top of the stack. So, basically what we need to do when we backtrack, so that sense of backtracking has been captured by popping out the element from the stack, and then whatever we have as stack top, we need to check the stack top for return to the previous node, and if the stack top is having any unvisited node, we need to process that. So, here after popping out B from the stack, we have D onto the top of the stack. So, again on checking D, we find yes, we have one unvisited vertex which is C. So, we are actually visiting the vertex C, marking it as visited, then we are you can say we are pushing out, we are pushing this D or a C onto the stack. So now the top of stack is having C, and the total stack is C, D, A and S. And please remember, we have already taken out the B. We have already popped out B vertex in the previous step. So now coming onto the top of stack, which is C, what we need to do, we need to check any unvisited adjacent node. So do we have any unvisited adjacent node as far as C is concerned? So essentially C is having S and D as its adjacent vertices, but none of them is actually unvisited, although they are adjacent but not visited. So again we need an unvisited vertex. So we do not have any vertex here. So we are not going to push any vertex on top of C. Rather than what will we do? Again we are at a dead end, we do not have any vertex to push onto the top of C, onto the top of stack, and then what we will see, we again keep on backtracking. So let us say we started backtracking from C. So backtracking here, I have told you that the sense of backtracking has been captured in terms of popping out the vertices from stack. So we have popped out C. Now at D, do we have any unvisited vertex? No, we do not have here. A, B, C all are visited vertices. Then we pop out D also. Then A as the top of the stack. A is having S and D, both are visited. So again we will pop out A also, and we will check S. Is S having any vertex which is unvisited? S is having A, B, C as 3 as adjacent vertices, but none of them is invisited, and we will be popping out S from the stack also, and essentially we have an empty stack. So we have started from C. The moment this steps of backtracking or the implementation of popping out from this step C. So C does not have any unvisited adjacent node. So we keep on popping the stack until we find a node that has an unvisited adjacent node. But in this graph, in this case, there is no such vertex which is having any which is available in the stack and having any unvisited adjacent node. So in this case there is none, and we keep on popping until the stack is empty, and then we have completed our algorithm of the depth first search. So depth first search algorithm essentially is a recursive algorithm which uses the idea of backtracking. So where is this recursion involved in depth first search? The moment we goes to we are going to backtrack until we are looking, we have found a particular base case. That is what the recursion is, and basically your depth first search involves exhaustive searches of all the nodes by going ahead, and then if it occurs onto a dead end, if possible, then if it is not possible to move in the depthward direction anymore, it will start the search by backtracking. So basically I can say it is the recursive nature of DFS, as I have already told you, which is implemented using stacks. So in order to give you a quick glance of the whole algorithm, I can say we need to pick a starting node, push it all adjacent nodes onto the stack, and then we will pop a node from stack to select the next node to visit. Then we push all its adjacent nodes onto the stack again, and we will keep on repeating this process until the stack is empty. But be very careful that you need to ensure that there will be there will be nodes which are already visited, and we need to ensure that the nodes that are visited are properly marked, so that we should not end up in moving into a particular loop, I can say, or in a cycle. So, if you can see the basic difference between the idea of BFS and DFS, what major differences we can chalk out here are the breadth first search is basically traversing the graph in a layer wise or level wise fashion, you can say, while depth first search is going to traverse the graph in a using a particular branch in the depth wise fashion, and it will keep on doing so unless you encounter a dead end. And if you encounter a dead end, it will keep on backtracking to the node, backtracking to the node till that particular node which is having any adjacent vertices which is unvisited. And for this backtracking notion, my DFS algorithm is using stack as the main data structure, while if you can remember that breadth first search is using queue as the data structure. So, because there is the difference between the order, or you can say there is the difference between the fashion or manner in which these two algorithms are visiting the vertices, the data structures used here are different. So, basically breadth first search is used in all the scenarios where you need to find a shortest path between two vertices x and y, any two vertices in the graph, while the depth first search says that you need to use DFS algorithm in in that situation if you want to check whether there is a path between two vertices x and y, if it exists. So, if you want to find that particular path, if it exists between two vertices, you need to go with the DFS algorithm, while in case of BFS we are looking for the shortest path, but yes, that shortest path may not be unique. This may be one of the many available shortest path between two vertices. So, yes, DFS and BFS both have their although they both are like traversal strategies, but they both are having their own application areas or application agendas, we can say. So, basically in this lecture we have covered what actually DFS is, taking it as a traversal algorithm, what are the main application areas it has, it is covering, in what all applications my DFS is going to be used, and what is the, you can say, strategy or how it performs as far as an undirected graph is considered. So, we have taken here two examples, both the examples were of undirected graph. So, this is what I can say about this lecture. So, DFS applications and its example on an undirected graph. So, hope you have enjoyed the lecture. Thank you.